Hello, everyone. This video is the first about determinants. Determinants are a quantity attached to a certain matrix that will help us determine whether the matrix is invertible or not. So let's start with the basic question of whether a general 2x2 matrix is invertible. To answer this question, what we want to do is to consider that matrix next to a block of an identity matrix, and then perform row operations to make the first half of this matrix equal to an identity. The first row operation that we want to do is to eliminate the entry C using the entry A above it. In other words, the row operation we want to perform is the second row minus C over A the first. The reason why we want to look at C over A is that if I take C over A times the first row, this becomes exactly C, and then we get B, C over A. Therefore, when we subtract this from the second row, you'll see that C minus C is 0, and D minus BC over A is the second entry, which is what I wrote here. I do have to complete the transformation throughout the whole row. So the other entry that changes is this 0 here that becomes a minus C over A in this side. Notice that here, to do this computation, we are assuming that we can divide by A. In other words, that A is different from 0. If that's not the case, well, then C is different from 0, or in which case we can switch the rows and perform the same process, but using C to eliminate A instead. If both C and A are 0, then the matrix A is not invertible. Because it has a column of zeros, and therefore it can't have rank 2, for example. So this process will work all the time. What is the next step that we have to take to complete the elimination? Well, is to use this entry down here to eliminate the entry B. We can only do that if the bottom entry D minus BC over A is different from 0. That's what we need. And we can rephrase this condition by multiplying both sides of this inequality by A as the quantity AD minus BC different from 0. This number is called the determinant of the matrix A. And in fact, it determines whether the matrix A is invertible or not. What happens is that A happens to be invertible if and only if its determinant is different from 0. When that happens, and I'll let you complete the Gaussian elimination that we started up here, you actually find a formula for the inverse, which is this formula over here. The inverse of a 2x2 matrix is the matrix you get by switching places with the elements on the main diagonal and changing signs to the elements off the diagonal, and then dividing everything by the determinant. That's the way I remember it. Let's apply this formula and this theory in a few examples. We have a matrix A given as such. First of all, let's try to determine whether it is invertible. The determinant of A is AD minus BC, which are the elements on the main diagonal minus the elements of the off diagonal. AD minus BC in this case is 1 by 5 minus 3 by 2. That's minus 1, which is different from 0. In other words, A is invertible. Let's now compute the inverse of A. A inverse is 1 over the determinant of A, by the formula above, times what I get by switching the entries on the main diagonal and changing signs to the entries on the off diagonal. If I want to complete this, remember that the determinant of A is equal to minus 1 in this case, so my final answer will be -5, 2, 3, and -1. The determinant flips the signs. Let's compute another example. Here's a matrix B. Let's check the determinant of B. This determinant is 1 times 6 minus 3 by 2. It's equal to 0, so B is not invertible. The next example is about the rotation matrix, which we saw in a previous video. Theta. Now let's compute the determinant of this matrix. It's the product of the elements on the main diagonal, which are cosine times cosine. I'll write that as cosine theta squared, minus the product of the elements on the off diagonal. But there's a negative sign here, so this becomes sine theta squared. This is a trigonometric identity, the Pythagorean identity. Cosine squared plus sine squared is always equal to 1, which is in particular different from 0, which tells us that our theta is invertible. Let's write the inverse of our theta. The way we can write this inverse is by switching places to the elements on the main diagonal, but those are the same, so nothing will change there, and then changing signs to the elements of the off diagonal. Now notice that since this is a rotation matrix, its inverse should be rotation by an angle minus theta, rotation by the opposite angle. Let's see if we find that believable. Rotation by the opposite angle is whatever I get by considering the rotation matrix with angle minus theta instead. Minus sine of minus theta, cosine of minus theta. And in fact, you can see that these two match by some of the definitions of cosine and sine, because we have that cosine of theta is the same as cosine of minus theta. In other words, cosine is an even function, and sine of theta is equal to minus sine of minus theta. In other words, sine is an odd function. We've dealt with determinants for 2x2 matrices. Our next goal is to extend this construction to bigger matrices, to bigger sized matrices. So the trick that we will use is to reduce the problem of computing a determinant for a bigger matrix to computing it for a smaller matrix. And we can iterate that until we reduce it to the problem of computing it for a 2x2, because we know how to do that. In order to do this, we'll define the following matrices. Given a matrix A, I've wrote it here with its entries, A11, A12, all the way up to ANN. We'll define the matrix Aij as whatever matrix I get by taking the matrix A, which is copied here, and deleting the ith row and the jth column from it. So the way we obtain Aij is by deleting the ith row and the jth column of A. This will be an n by 1, n minus 1 by n minus 1 matrix. It will have one fewer row and one fewer column. Let's have a look at an example. Suppose that my matrix A is the one written here. Let's compute some of these deleted matrices. A12 is the matrix I get by deleting the first row and the second column. In other words, A12 will be, maybe I'll write it here, 4, 7, 6, 9. A23 is the matrix that I will get by A23 is the matrix I get by erasing the second row and the third column. In other words, it's 1, 2, 7, 8. A11 is the matrix obtained by erasing the first row and the first column. 5, 6, 8, 9. Let's play this game with a smaller matrix. If we start from a 2 by 2, then A11 is what I get by deleting the first row and first column. So A11 is equal to D, just the entry D, or the 1 by 1 matrix D, which is the scalar. A12 is what I get by erasing the first row and second column, which is the scalar C. And now I want to point out, before we move on to determinants of bigger size matrices, something that happens in the formula of the determinant of a 2 by 2 matrix. This determinant is given by A, which is the entry A11, times the determinant of the reduced matrix capital A11, which is D. And here we have minus B, which is A12, times the determinant of the matrix A12. So let me write it here. A formula, an alternative way to write the determinant for a 2 by 2 matrix is this formula here. Now we'll take this formula and extend it to a bigger sized matrix. We will just move along the first row of the matrix and look at its entries, A11, A12, A13, all the way up to A1n, and multiply each one of these entries by the determinant of the reduced matrix with corresponding indices. So A11 will be multiplied by the determinant of capital A11, A12 will multiply the determinant of capital A12, and so on. But there's something that I have to bring your attention to. Every other term has a switched sign. So we start with a plus here, and then it becomes a minus, plus, minus, and so on until the end. Since I don't know what n is, whether it's even or odd, the way I have to represent an alternating sign is a -1 to the n plus 1. If n plus 1 is even, this becomes a plus. If n plus 1 is odd, this becomes a minus. To make this formula look a little bit cleaner, people define the cofactors of A in the following way. The cofactor of it, the ijth cofactor of A is defined as the determinant of the reduced matrix Aij, but adjusted with a sign. And the sign will have the adjustment that depends on the indices. So the cofactor ijth is -1 to the I plus j times the determinant of capital Aij. If we use this formalism, theseCij's, then the formula for the determinant becomes a little bit nicer. We can encompass all these smaller determinants in here into the letters C11, C12, and C13, and all the signs here appear as plus because the minuses are inside the cofactor expansion. This neater formula is called the cofactor expansion of the determinant. And you see that now the determinant works for any matrix because we can just reduce the question of computing a determinant to reducing it to computing a smaller determinant, those of the reduced matrices. So we can keep doing that until we get to computing 2 by 2 matrices, which we know how to do. Let's have a look at an example. we'll compute the determinant of this matrix A, and then we'll do it with a 4x4. To compute the determinant of this, we can use the cofactor expansion. The cofactor expansion will prescribe me to do, I will go along the first row, so it's going to be 1 times the determinant of A11 minus 2 times the determinant of A12 plus 3 times the determinant of A13. And before we move on with this computation, let's look at these three cofactors. So A11 is the matrix I get by canceling the first and second row. So this is 5, 6, 8, 9. A12 is what I get by canceling first row and second column, 6, 9. And A13 I get by erasing the third column. So it's 4, 5, 7, 8. Let's compute these determinants. Determinant of A11 is 45 minus 6 by 8 is 48, so that's -3. The determinant of A12 is 4 by 9 is 36, minus 6 by 7, which is 42, that's a -6. And the determinant of A13 is 4 by 8, which is 32, minus 35. So that's a -3. Let's plug these numbers in here. We get 1 times -3, minus 2 times -6, plus 3 times -3. And this becomes -3 plus 12 minus 9, which is equal to 0. Okay. Let's have a look at this other matrix here. Right there, it's 6 before. Give me a second. Okay, I double checked my computations and they are fine. Let's move on to the next example. This example here is a 4x4. So if we wanted to compute its determinant, we would have to use the same cofactor expansion. So I would do this entry times the determinant of the matrix I get by erasing first row and first column, minus this entry 2 times the second cofactor, erasing the second column as the first row, and then I would add plus 3 times the determinant by erasing the third matrix, and then the last one plus 4 times the cofactor, erasing the first row, the first row and the last column. That's what I wrote here. However, it would be much nicer if instead of looking at the first row to do our cofactor expansion, we could follow along the last row, because the last row has lots of zeros. So if this was the case, and I were to expand along the last row, my cofactor expansion would look like this. 0 times the cofactor corresponding to erasing the last row and the first column, C41, plus 0 times C42, erase last row, second column, plus 0 times C43, plus 1 times C44. So the only term that I would have to compute if I were able to expand my cofactor determinant along the last row would be my last cofactor, C44. Computing C44 is not that bad. By definition, it's -1 to the 4 plus 4 times the determinant of this matrix 3 by 3. And by just how I set things up, that matrix is exactly the matrix that we just computed. So this is 1 times 0, which is 0. And therefore, the determinant of the matrix A is also 0. That is the last thing that I want to mention in this video. In fact, we can have row cofactor expansions starting and following any of the rows. The definition we gave above was with the first row, but it actually works with any one. And that's what this formula here is telling us. We don't have to expand along the first row, which would have made A11, C11, plus A12, C12, and so on. A1n, C1n. This would be the first row. Instead, we can start at any row and replace all those ones above with i's in the row index. And we still get the same result. An example of why this is useful is what we just saw. In this matrix up here, it's much more convenient to use a cofactor expansion along the last row rather than the first one. This is the end of the video. In the next one, we'll explore some geometric significance of determinants, and then we'll move on to properties of determinants.